for this session under the lab, which is called BIOS 611 lab exercise. And you'll see it open up something like this. Let me hide some of that extraneous stuff so you don't have to look at it. Get rid of the ribbon so you have a little bit more room to work. I'll make it a little bit bigger. Okay, so let's talk about this idea of taking distinguishing between a population and samples. Okay, when we take a sample, if we want a representative sample, we want our sample to look like the population. We want it to represent the population. So a lot of times we very rarely, we very rarely get to know everything about a population. Anybody think of a situation where we know all about a population? Okay, where you know, say the ages, the number of people in a family, the census, exactly. Once every 10 years, we do an actual count. Yeah. Prisoners too, yeah, prison population. You know everything about them, their health status, their ages, their heights, their weights, and so on and so forth. That's an unusual situation. In most cases, we don't really have the resources to know all about a population. So the way that we learn about a population is by sampling that population and hoping that that sample is representative of what the population looks like. For instance, that the mean of the sample approximates the mean of the population, whether it's age or BMI or whatever, right? So let's take a look at this, what happens when we take samples from a population. First thing I have is I have a population of 100 people here, 100 measurements here. Okay, now these could represent anything, but take my word for it for the moment. But it's a normally distributed population, approximately normally distributed population. I actually have the file that this was created from in Excel. Okay, population of 100, and if I want, I can take this and I can actually calculate what the mean and the standard deviation of this population are. I'm going to spread this out a little bit. Okay, so average, parentheses, and let me see if I can't get it to scroll so I don't have to go crazy. So the average for this population is 50, about a little over 50. And the standard deviation for this population is, okay, so what we get is about 9. So we got an average of about 50, and we have a standard deviation of 9. Now this is very nice, but it's a very rare situation. We very rarely know everything about a population like this. Okay, so let's take a look at what would happen if we took a sample from a population, whether or not it would really be representative of the population. Okay, so what I'm going to do is I'm going to take randomly sample 9 people, 9 measurements, whatever we want to call them, from this population. Okay, imagine this population really 1 million people. I'm going to sample 9 people out of this population. And you could say, like the phone books, twirl the pages, put your finger in, or turn the globe, and put your finger down. But that doesn't really work. That's not really random. If you're left-handed or right-handed, you might get a different sample, and so on and so forth. It might be skewed. So there's a lot of techniques that you can use to randomize your selection from a population. One of the ways you can do it is to assign numbers to everybody in that population, or assign numbers to the group you're going to sample from. And you can refer to a random number table. Now, these are tables that are assembled in textbooks. In fact, there might be a random number table in our textbook, but these numbers have been either computer generated or generated based on some natural random event like radioactive decay or something like that, but they're generated so that these numbers have been created randomly. So we can identify each one of the numbers in this grid by a row and a column. So what I'm going to do is I'm going to take these randomly generated numbers and I'm going to start anywhere. I'm going to start, say, at the beginning of this 3rd row. So the first 2-digit number I see there is 65. So I'm going to call that row 6, column 5. So my first number that I'm randomly selecting is row 6, column 5 would be 54. And the next number I'm selecting is going to be row 2, column 8. which would be 51. Now, what I'm going to do is I'm going to ask you guys and the guys online to use this table to randomly select 9 people from this population. Okay, each one of you start in a different, don't start in the same spot I did, because then you'll just wind up with the same sample, of course. But start in a different spot, and when you get ready, give me a yell, and I'll record what your result was. Oh, got away. Okay, I'll do my own. What did I say, 6? 5 was 54. And 2 and 8 was 49. I think it's going to be easier for you guys to do it than me, because I'm going to go straight across. That'll be a 59. 9 would be 47. And 71 and 98. Okay, 40 and 43. And let's see, where was I here? 98, 12, 13, and 85. 46, 12, 13, 59. And I forget what the last one was. It was 85. 85. It was 55. Okay, so I've got a short one. Yes.
9.
I'm sorry?
You said 9.
9, yeah. There's going to be a reason for that. Mostly, some of you actually probably have already realized what the reason that I picked 9 is, but we'll see in a second. 85, 30. And 3 zeros, 52. Okay, I got my sample size of 9. Reduce the size just a little bit. I can see my on screen. Okay, you guys want to start feeding me numbers? For this one, the average is 49. I'll just make that bold so I know it's the average. Okay, pretty good, right? 49. Pretty close to what my real population mean was. Don't tell me an old man like me got this done the fastest, right? You got it. No,
You want the average?
yeah, the average. 52. Okay, there we go. See if anybody online has posted in yet. Okay. Oh, what's that?
49.
54.
Wait. 49. What did I miss?
54.
53. 54.
52.
52. Anybody else? How about you guys? Oh, 52 online. 46. Anybody else? Okay, got a 94. I don't think you got a 94. Brigida, give that a try again. I don't. It's not possible to get a 94, right? Because there's not a single number that's as big as 94. So we want the average of the 9 numbers. 53.55. Let's call that 54. Okay. few more. Okay. I'll wait for one or two more, I guess. Any other contributors? Okay. I hope I didn't confuse you with this description of how I was using that random number table. 49. Good. 45.4. I'm going to call that 46. Okay, I think I have enough for now. Okay, if you throw in another couple of numbers while I'm talking, we can always add them on. Okay, so let's take a look at what we have here. We have a sample. We have a new sample. We have taken a sample of size 9 from this population 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 times. We've taken a sample from this population 12 times. We have 12 numbers that we have. Those numbers are repeated calculations of the mean from that population for a sample of size 9. Now we can take those numbers and make a new distribution, right? What would we expect the mean of these samples to be? 50. We'd expect it to be close to approximate the mean, right? Just like we would expect any one of them to approximate the mean, and especially as the samples got bigger, we would expect the average for all of these samples to approximate the mean. What about the variability? What about the standard deviation of these numbers compared to the standard deviation of the population? Would we expect the standard deviation or variability to be narrower or wider? Narrower. Why? Because every time we take a sample of size 9, we're going to get a number that's closer to the mean than a typical randomly selected single person from the population, right? Population could be 30 to 70, but we wouldn't expect, if we're taking samples of size 9, to get those extreme values of 30 and 70 for 9 people averaged together. Yes?
The sampling distribution, does every single averages that you take to be the same sample size?
Well, well, actually, we're going to we can make a new distribution of sample size 16 or sample size 25. We can choose any sample size that we want, but when we're examining the properties of a particular sampling distribution, we want all of the samples to be the same size. So this is right now is sample size 9, right? Okay, so let's actually calculate the mean here. So the mean is equal to the average of all of these values. And it comes out to, average, parentheses. My keyboard's a little sticky here. Come on. Okay, let me try this again. I think it should ignore the empties. Yeah, it comes up to 50.25, pretty close to what the population mean was. Now notice, individually, they're not that close, right? We got values as high as low as 46 and as high as 53. So individually, they're not that close, but the average of repeated samples over and over again. So as the number of times that we sample this gets bigger and bigger and bigger, if we repeat this sample, our distribution is going to get closer and closer to the mean. Let's take, what was the standard deviation before for the population? It was approximately, yeah, it was approximately 9, right? Let's take a look at what the standard deviation is now. And this is for the new sampling distribution. The standard deviation for these sample means of size from a sample of size 9, and it comes out to be 3. I can't believe this. We do this every semester, and it never comes out to be 9 and 3. No, it never comes out to be the mean in 3. So what happened here? The standard deviation of the sample is, what's the relationship between the standard deviation of the mean, sample mean, the population mean, and the sample mean? It's the square root, right? So there's an interesting relationship going on here, right? The standard deviation of the sample distribution is narrower, and there's a relationship between the two of them. We're going to see that the relationship is that as the sample size gets bigger, the variability in the sample distribution gets smaller. If we took a sample size of 25, it would be equal to the standard deviation of the population divided by the square root of 25. If we took a sample size of 49, it would be equal to the standard deviation of the population divided by the square root of 49. Right? So there's that relation. It's that sigma over the square root of n. We see that actually demonstrated when we did this example. And to be honest with you, it normally doesn't come out that nicely, but it did this time. Right? So in this case, the standard deviation of that sample distribution would be equal to the standard deviation of the population over the square root of the sample size, which was 9, which is 3. So it actually comes out almost perfectly. Right? And trust me, that was all luck. We do this every semester, never comes out quite right. So we got lucky this semester. Okay, so at any rate, and you guys generated the random numbers. So at any rate, so we know we have that population. But in order to make this work, what do I need to know? Notice that I used something that was a parameter rather than something from the sample. Right? What did I say? The standard deviation of the sampling distribution is equal to sigma over the square root of the sample size. Right? What's sigma? Sigma is a standard deviation of the population. It's a parameter. I just told you that we very rarely know the population standard deviation, population mean. What makes you think we're going to know the population standard deviation? So most of the time, we're relying on estimating the population standard deviation by calculating the sample standard deviation. But for the time being, for today only, we're going to assume in all the problems that we're going to go through from now on, we're going to make believe that we know the population standard deviation so that we can use this rule with impunity. Later on, we're going to be making corrections for the fact that maybe we don't know it perfectly. We have to calculate it some other way. We have to estimate it based on the sample distribution, the sample that we take, right? But for the time being, we're going to make believe that we know that even though we don't know the population mean, we do know the population standard deviation. So that I can use this relationship. The standard deviation of the sample means is equal to the standard deviation of the population, sigma, over the square root of the sample size. Okay, so now I need something. I'm calling the population mean the population variability is standard deviation of the population, or sigma. I need a new name for the standard deviation of these sample means. So what do we call those? Came up before. Let's call those the standard error. Right? So when we say standard error, we're talking about the standard deviation of these numbers, which represent the variability of these repeated samples of that size over and over again. That's our standard deviation. It's our standard error. It's our standard deviation for the sample distribution.